Hello. Today we're going to talk a little bit about refraction. I want you to start by looking at a video I took over 20 years ago as my family was visiting the Denver Zoo, and I saw something in the polar bear exhibit. I thought it was kind of interesting. I videotaped it, and we'll see if we can explain that by the end of this. If you'll notice here, the polar bear's head is at this location, but his body is at a very different location. The question is, why is that the way it is? It seems kind of strange. So that's what we really want to explain here today. Well, I told you before that the speed of light, c, is 3 times 10 to the 8th meters per second. It's 2.99 some change, but pretty close to 3. Okay. Now, I'm going to give you more of the story. It's not always that. That's in a vacuum. Okay. In a vacuum, it's pretty close to that value. But in other materials, it actually slows down. And the amount it slows down is a measurable quantity in the proportion. So what we do is refer to the index of refraction. And so what we have is we have a relationship, is that the index of refraction, we're going to give it the letter n, is the speed of light in a vacuum divided by the speed of light in that material, v sub n. Okay? Now, the speed of light in a vacuum will always be larger than the speed of light in the material. So this ratio will always be larger than 1. They will always have the same units, and that units will cancel. So our index of refraction will be dimensionless. It will just be a number. Okay. So now you look up the indices of refraction, okay, often referred to as a refractive index. Typically look up a chart, and here is a chart with some values on it. Of course, you'll notice ones that are notable. Air has an index of refraction that's really close to 1, and therefore the speed of light in air, when you take 3 times 10 to the 8th and divide it by 1.000293, you're going to get really close to the same value. So we just use the speed of light in air to be 3 times 10 to the 8th. It's a good enough approximation. Okay. Other ones that are notable that you use a lot, water. Okay. Speed of light, index of refraction for water, 1.33. So if you want to know, hey, well, what is the speed of light in water? Okay, well, let's see. Here's things that you should be able to do when it comes quiz time. You should be able to find the speed of light in a particular material. So if you want to find the speed of light in water, we would take 3 times 10 to the 8th meters per second. And now we're going to divide by the n. So we're going to switch these two variables, multiply both sides by v sub n, divide both sides by n. And our n, we look up here, 1.333. And when you do that calculation, you get around 2.25 times 10 to the 8th meters per second. So that would be the speed of light in water. Now this, you could have different types of water, different amounts of salinity. So this is a very brief chart. You could have much more elaborate charts with more materials on it. You could say, well, I have a material and I want to identify this material. Well, one of the ways you can identify materials is by their index of refraction. So let's say I know the speed of light in that material is 2 times 10 to the 8th meters per second. And then if we put C on the top, which is 3 times 10 to the 8th meters per second, of course, the meters per second cancel, 10 to the 8ths cancel, and 3 divided by 2, of course, is just 1.5. And so you'll notice some materials that are close to 1.5. A lot of glass is in the ballpark of 1.5. So that's not uncommon. So water is a little bit smaller index refraction of 1.333. A lot of the glasses are in the area of 1.5. But then you get some larger ones. And for example, diamond, one of the great properties of diamond comes from the fact that it has a very large index of refraction. Right? Now, to give you more of the story here is you'll notice on the bottom of this chart, all the values are for light having a wavelength of 589 nanometers in a vacuum. Okay, now the 589 nanometers, if you come down here, 589 is kind of a yellow version of light. So what we find is index refractions are not the same for all colors. Different colors travel at different speeds, but they're very slight changes. Okay, so for example here, this chart is for ice. Okay, now if you look at ice, this chart here says the index refraction is 1.309 for the index refraction of ice. Well, this graph here shows that the index refraction 1.309 would be somewhere around here, which of course would line up with kind of a yellow form. Not exactly the same temperature, but what we'll find is that the index refraction is different for each color. The reds actually have a low index of refraction. This is a low N. And the blues have a N which is a higher value, high N, which means that if you want to find the speed of light for the red light, when you take 3 times 10 to the 8th and divide it by a low value for N, when the denominator is smaller, the value is higher. So this is fast. Red light is actually going to be faster slightly, just slightly, than the blue light, which is going to be slightly slower in that material. Okay? And as a result, it's going to cause some interesting things to occur, and we're going to see that a little bit later. Okay? But we want to know that the index refraction, although a chart like this will give kind of average values, those values can differ slightly along the spectrum. And this part of the graph is just the visible spectrum. We couldn't continue this out in the ultraviolet or the infrared or wherever it is. But we're interested in that slight change because you're going to find some interesting things that you've seen before and maybe not know why this occurred. Okay, so now that still hasn't gotten us to the point where we can explain what went on with the polar bear, but it's got us one step closer. Now what we're going to move to is we're going to move to what's called Fermat's principle. Fermat was a French mathematician and a lawyer, and he came up with some mathematical concepts, some related to calculus, some related to physics and other topics. And so there's a common misconception, and that polar bear video shows that we get confused by it, and because we live with an assumption, and there's an assumption that light travels in a straight line. And that just is not always true. Okay? There's a better way to describe the path that light takes. Light takes the path of least time. That's what we want to remember. That's the one idea. Light takes a path of least time. Now, if the medium is consistent, then the path of least time is a straight line. However, if there's a boundary, if it's changing from one medium to another, the speed of light could change, and that wouldn't necessarily give you the best time trying to go in a straight line. So there's an easy way to think about this. So it's going to seem kind of a strange analogy, but that's okay. I want to pretend that you're at a beach, going to a lake, and you're on the beach, and here's the sand, and here's the water. And there's a lifeguard stand. And out here, there's a person, and they're in some need of help. And the question is, the lifeguard jumps out of his stand and takes off for the person struggling in the water. What is the best path they should take? Do they take a straight line, the shortest distance? No, if you're struggling out there, you would like the path of least time. And so what you have to do is you have to realize that for most people, they can run faster in sand than they can swim in water. And therefore, you have to think of this as a fast medium and a slower medium. Okay, now if you were running on the sand versus a boat in the water, well, then that could be reversed. But you have to understand which, in this context, which is the fast medium, which is the slow medium. And so what happens is the lifeguard should now take a different path, not a straight line path. They would go a larger distance in the sand, and then they would take a shorter distance in the water. Now, if this was all the same material, if it was sand the whole way, they would simply go in a straight line. If they were going to get into a boat and take off, then they would want to come down and do a shorter distance in sand and then go here. So there's three different paths depending upon what the context is. This here, we have the fast versus slow. This path here would be if this is the slow medium and this is the fast medium. And then the straight line would be if they are the same speed. If it was sand all the way or water all the way, they would just go a straight line. Of course, this is assuming no currents involved or anything. So we have these different paths, and these are the paths of least time. Okay, that's the criteria here that we're interested in, is the path of least time. Now, how does this relate to light? Well, light travels the path of least time. And so when it gets to a boundary, light traveling from one point to another can bend. And which way will it bend? Well, it either bends towards the normal or away from the normal, depending upon whether it's going fast, from the fast medium to slow, or slow to fast. And so as we do this, we are going to draw at the point where the boundary is, either one of these cases, or in three, we will draw a normal line. A line which is perpendicular to the boundary at that point. You'll notice in the same, there is no change. It goes in a straight line. But here we have what's called the angle of incidence. And then down here we have an angle of refraction. And the angle of refraction is smaller than the angle of incidence. So we say that the ray has bent toward the normal. It's gotten closer to the normal. Over here, here's our angle of incidence. And here is our angle of refraction, not reflection, refraction. And we'll notice the angle of refraction in this context has gotten bigger. So we say it's bent away from the normal, okay? So now let's take a look at it in terms here. Here we're going from air into water, and we know the index refraction for air is close to 1, and water is 1.33. So we're going to call that N1, the first medium, and 2, the second medium. So we go from, so we have to keep in mind, low index means it's a fast medium, and the high index means it's a slower medium. It's relative. You could put glass against water, and all of a sudden the water is the faster of the two mediums. But in the context of air, water is the slow medium. And so as the light ray comes in, here's our angle of incidence, theta I. Here's our angle of refraction, theta r, and notice it's gotten smaller. We see the normal there, and the angle, the line, the light ray has bent toward the normal. Now this is completely reversible. So now if you're out in the water and you want to get back, you would take the same path to give you the path of least time, and light rays will travel the same path. If your light ray traveling here and hits a mirror, it would come back and follow the same path. It would take the path of least time. The problem is we tend to naturally think light travels in a straight line. So we think along this line right here. And this is the problem with the polar bear. We're thinking along one line when the light is actually, part of the light is taking a different path. And that difference between what we think is going to occur and what does occur often results in something which seems a little bit strange. Okay, so now we don't see this problem all the time because normally the glass that we look through, like windows, are thin and they have parallel sides. And so if they have parallel sides, then what we find is as the light ray comes in, it bends, in this case going from, like say, air to glass, it bends towards the normal. Then when it gets to the other side, it bends away from the normal. And these two light rays, the original light ray and the final light ray, they're not the exact same light ray, but they are parallel to each other. If the two sides of the glass plate are parallel, then these two light rays are parallel. And if the glass is relatively thin, especially in comparison to the distance you're talking about, you really would have a hard time noticing that. You typically don't notice that. Now, if the surfaces of glass are not parallel, such as like in your glasses, they're curved, then the light rays can be bent a little bit, and that's what people who make glasses, they shape in such a way to get the light rays to bend just the way you'd like them to go. But the key things we got to know is that when you go from a fast medium to a slow medium, the rays bend toward the normal, and if you go from the slow medium to the fast medium, then they bend away from the normal. That's the key phrase. Right. Now, let's make the plot thicken a little bit more. You've seen this, a prism. Okay, well, here we go. Light ray comes in. Let's say white light comes in, has all the colors of light, and there's the normal. And the amount it bends is dependent upon the index refraction. But we remember that every color has a very slight difference in indices of refraction. This picture exaggerates it just so you can see it. The difference is very slight. And the reds will be the fastest ones in the medium, and the blues and the violets, the high frequencies, they slow down the most. And so the reds bend a little bit, and the blues bends more, and all the colors in between, they spread out. And then we have them leaving the other side. We could draw a normal on the other side. Of course, we'd have to draw a normal for each of these lines, but so the normal exists as well, but a lot of them you'd have to draw if you want to draw them all. They will bend away from the normal, and we get this spreading. So we get this color spreading. And this is why diamonds are used in jewelry. A couple reasons. One is they're so incredibly hard, so they're durable. But another reason is the index refraction for diamond is so incredibly large that it causes the light to spread out the most. And therefore, when you look at a light hitting a diamond, it gives you that rainbow effect because it gives you all those colors. It gives you that prism, spreads out all the colors. And the reason we get that spreading out of the colors is because every color will have a slightly different index refraction, and therefore will get bent a little bit different. Okay. Now, let's see if we can apply this a little bit to some everyday occurrences, or maybe not completely everyday, but let's say you go swimming in a pool this summer, and as you go swimming, hopefully the water is not green, And you ever jumped into a pool and you realize the pool is deeper than you thought it was. Okay, well, why is that the case? Well, what happens is a lot of times we take our clues on how deep the pool is by looking at, let's say, the corner. That means a light ray coming from this corner comes out, hits the water. This is the water, so this is the slow medium. Hits the air, which is the fast medium. There's a normal. The light ray bends away. Let me see if I can draw an actual straight one. Straighter line. Bends away from the normal. And let's say that you are over here and your eye, this is your eye, and you see that light ray. Now, there's lots of light rays coming off of this point. We're not interested in all the light rays. We're just interested in that particular light ray, which happens to come from there and hits you in the eye. Okay. Now, the problem is, if you think in a straight line, you will think that this point is actually here. I've exaggerated the angle a bit. So you're going to think the pool is that deep when it's actually this deep. It wouldn't be in this case. It looks like it's 2.5 to 3 times larger, but it will be that angle that we get. Here's our, in this case, as the light ray comes out, this is the angle of incidence, and that's the angle of refraction. Okay, so it comes in at this angle. As it heads to your eye, it's that angle. And therefore, if you think in a straight line, you think the pool is this deep, and it's actually deeper. So you jump in that water thinking, oh, I think it'll be up to my chest, I have no problem. And then all of a sudden you realize it's over your head. And that can be the problem. That's why you want to read on the side of a pool that's deep. If it says how deep it is and realize it's 5 foot and you're 6 foot tall, no problem. But if you're just, if it says it's 5.5 feet deep and you think, oh, it only looks like it's 5 feet, well, you may be off by a little bit, and that could be a problem. Okay. Another example. Let's take a look at, let's say you go spear fishing. And once again, maybe you haven't gone spear fishing. Around here, most people don't go spear fishing, but I have on occasion seen people who go bow fishing. And so they fish with a bow and arrow with a string tied to the arrow, and they shoot it and then they pull the fish back. But you have to know where to aim on this. So the same sort of thing. Light ray, we're interested in the light ray which comes off of the light ray that comes off of the fish. And a light ray coming off of the fish, here it comes and then it bends away from the normal, hits you in the eye. There's lots of light rays that come from the fish. We're only interested in that particular light ray which hits you in the eye. Unfortunately, we tend to think in straight lines, and so we tend to think that the fish is here. And so, but the fish is not. The fish is actually at a slightly different location. So, if you find yourself in a situation like that, the key thing is know, okay, I know that is not exactly where it's at. It's going to be a little bit off, okay? So we would aim a little bit closer to you. Now, how does that relate to the polar bear? Well, the polar bear, when you see his head, the light ray is traveling almost all in air. It goes through the air, then it hits the glass, and then it goes through the air again. And so that's almost in a straight line. So this is kind of what we think in terms of where the head of the polar bear may be, where this would be representing where the body of the polar bear is. Okay? And therefore, there's a difference between the head and the body. So now, let's go back and finish up looking at that video. So when you see the bear all in the water, he looks together. Oh, but now his head looks disconnected. Also notice his body, which is in the water, looks closer. Now as the bear gets closer to the window, there's a less difference, and so you don't notice it as much. Okay. So hopefully you realize the index refraction. What are the things you need to know for the quiz? Okay, well, when it comes to the quiz, you should know how to calculate the speed of light in a material based on the index refraction and find the index refraction based on the speed of light. You should be able to do that. And you should know when it bends towards and away. Okay, if you're going from fast to slow, it bends towards the normal. If you're going from slow to fast, it bends away. Those are the key things to focus on. Hope this helps.